Are there any special vectors that only get scaled? Are there any special vectors that only get scaled? So 3 by 3. So if you simplified 3 of 1 by 1, so same case. So scaling only here form. That's why special vector only get it scaled. This is the special vector. Mx m vector x vector equal to 3 3. Simplify. For this special vector, multiplying by m is like multiplying by scalar. This m is multiplying by scalar. For the special vector, multiplying by m is like multiplying by a scalar. 1 comma 1 is called an eigenvector of m. 3. The scaling factor is called the eigenvalue. The 3 is called the eigenvalue. 1 comma 1 is called the eigenvector. This is the eigenvector. This 3 is called the eigenvalue. Called the eigenvalue associated with this eigenvector. Actually, generally, here in this positive position, which one is coming in the live, then that value only we can take as eigenvector, eigenvalue in any matrix. Are there any other eigenvectors? Yes. The easiest way to find is with the MATLAB's Eig command. E power 1, E vector 1, 1, E vector 2, minus 1.5, 1. Exercise. Verify that minus 1.5, 1 is also an eigenvector of M. Note, eigenvectors are only defined up to a scale factor. Eigenvectors are only defined up to a scale vector. Eigenvectors are only defined up to a scale vector. Yes, eigenvector only a scale factor. Scale factor is the eigenvector, nothing but a scale factor, you can say, up to scale factor. Conventions are either to make these unit vectors or make one of the elements 1. Conventions are either to make these unit vectors or make one of the element is 1. Okay, so step back. Eigenvectors obey this equation. Me vector equal to lambda E vector. Solve. M minus lambda 1 of E vector equal to 0 for E vector not equal to 0. So set determinant M minus lambda 1 vector equal to 0. This is called the characteristic equation for lambda. In general, for an n cross n matrix, there are n eigenvectors. Examples: coupled differential equations. Coupled differential equations dx by dt equal to mx1 plus I vector. I didn't mention vector. Dx vector divided by dt equal to m vector x vector plus I vector. Calculate the eigenvectors and eigenvalues. Eigenvalues have typical form lambda equal to lambda plus lambda I capital I small I, where I small I is the root of -1. So the corresponding eigenvector component has dynamics e power lambda t equal to e power lambda rt into e power I lambda caps I t. The first e power lambda rt is the lambda r less than 0. It is the stable one. Lambda r greater than 0. We are mentioning it is the unstable. Lambda caps I not equal to 0. It means this one oscillations of angular frequency lambda e power I these steps full equal to cos lambda it plus I sin of lambda it. Here this lambda r is less than 0, stable. It means stable. Lambda r stable. If less than 0, it means stable. If greater than 0, it means unstable. Below 0, less than 0 is stable. It means here lambda I not equal to 0. Oscillation of frequency lambda I e power total e power I lambda caps it equal to cos lambda it plus I sin lambda it. Practical program for approaching equations coupled through a term mx. Eigen in MATLAB. Okay. Step 1, practical program for approaching equations coupled through a term mx. Step 1, find the eigenvalues and eigenvectors of m. Step 2, decompose x into its eigenvector components. Step 3, scale each eigenvalue component. Step 4, solve for C and transform back to original coordinates. Okay. Here practical program for approaching equations coupled through a term mx. Step 1, find the eigenvalues and eigenvectors of M. X vector equal to C1 e power E1 E vector 1 plus C2 e power 2 plus Cn e power minus n. Step 2, decompose X into eigenvector components. 3, stretch scale each eigenvalue component. 4th, solve for C and transform back to original coordinates. Original coordinates. Here example, this one. So this is the equation, sorry. This is the equations. So here in this row C1, C2 up to Cn column, E1, E2 up to En row. So EC or C vector equal to E vector power minus 1 X. Practical program for approaching equations coupled through a term Mx. Practical program for approaching equations coupled through a term Mx. Find the eigenvalues and eigenvectors of M. Decompose X into its eigenvector components. Stretch scale each eigenvalue component. Step 4, solve for C and transform back to original coordinates. So here X equal to C1 e power 1 e vector 1 plus C2 e2 plus up to Cn e power n. So equal to E vector C vector. Here putting it all together. M equal to M vector equal to E vector E inverse vector. Where step 1, so row, so diagonal matrix lambda 1 lambda 2 lambda n, MATLAB like this, Eigen M, putting all together. So again next step, from this putting it all together continuation, M vector X vector, sorry, E vector E inverse vector X. So here step 4, transform back to original coordinate system, this one. Here scale by lambda I along ith eigen coordinates, this one. Here these steps, both step 2, transform into eigen coordinates,